Good morning, students. Myself, L Nagaraju, Assistant Professor in Mathematics, Department of Science and Humanities, the National Engineering College, Medboli, Meerpet, Hyderabad. Today, I would like to explain Green's theorem and problems on Green's theorem and also applications of Green's theorem. So, Green's theorem, problems of Green's theorem, applications of Green's theorem. Okay, first of all, Green's theorem statement. So, Green's theorem in a plane. What is the Green's theorem? Transformation between line integral and double integral. Transformation between line integral and double integral. So, statement of the Green's theorem is if R is a closed region in xy plane bounded by a simple closed curve C, if M and N are continuous functions of x and y having continuous derivatives in capital R, then integral over the closed curve C, mdx plus mdy is equal to double integral over the region R, dou n by dou x minus dou n by dou y, dx dy, where C is traversed in the positive direction, that means anti-clockwise direction. So this is the statement. So here R is a closed region, so which is bounded by a closed curve in xy plane. Here m comma n are continuous functions of x and y having continuous derivatives in R. Then this is the condition. Integral over C, closed curve C, mdx plus ndy is equal double integral over the R, dou n by dou x minus dou n by dou y dx dy. So where C is the traverse in the positive direction or anti-clockwise direction. Anti-clockwise direction. So this is the diagram. This is the diagram related to Green's theorem. So here the R is the region, so which is bounded by the closed curve C. Okay, in XY plane. Okay, so here we have one note. Okay, so note that Green's theorem converts a line around a closed curve into a double integral and is a special case of Stokes theorem. So we know that the Stokes theorem statement. So from this, we will get the Green's theorem condition. So let M is equal to M I bar plus N J bar and the position vector R bar is equal to X I bar plus Y J bar. So which implies we can write D R bar is equal to dx I bar plus dy j bar. So then, so we have F bar and we have dr bar. So the dot product of F bar and dr bar. So F bar dot dr bar is equal to mdx plus md. So curly F bar is equal, so we can write or del cross F bar is equal determinant of I bar, j bar, k bar, dou by dou x, dou by dou y, dou by dou z, m n 0. So this is equal, we will get dou n by dou x minus dou m by dou y into k bar. Okay, k bar. Therefore, we know that integral over C, F bar dot dr bar is equal to integral over the region R curl F bar dot n bar dr. So where n bar is equal to k bar for xy plane and dr is equal to dx dy, surface of the plane. So and curly F bar dot n bar is equal. So this is equal. Curly F bar is equal. We having dou n by dou x minus dou m by dou y into k bar dot n bar is equal to we have k bar. So k bar dot k bar is equal to 1. So we are getting curly F bar dot n bar is equal to dou n by dou x minus dou m by dou y. So which is same as Green's theorem. Again, we have one more note. Area of the plane, area of a plane, region R bounded by a simple closed curve C. So let here n is equal to x and m is equal to minus y. So which implies dou n by dou x is equal to 1, which implies dou n by dou y is equal to minus 1. So substituting these values in the Green's theorem condition, we are getting. So then substituting these values in the Green's theorem. So integral over C x dy minus y dx. This is nothing but m dx plus n dy. So here in place of m minus 5 we have, in place of n we have x1. So this is equal to double integral over r dou n by dou x is equal to plus 1 minus of minus 1 is plus 1. That is dou n by dou n into dx dy. So this is equal to 1 plus 1 is equal to 2 is writing outside. So this is equal, we will get 2 into double integral over r dx dy. So we are, this is equal to area of the region. So that is, we are taking capital E. So this is equal, we are writing 1 by 2 integral over this C x dy minus y dx. Okay. Now coming to the problems. First one. So evaluate. So here we will get two kinds of problems by the solving Green's theorem. So one is evaluate and the one is verify for any problem. So when we are when evaluate given in the problem, we have to solve only right hand side of the right hand condition of the Green's theorem. Okay, so here the right hand condition, what is the right hand condition? Double integral over r dou n by dou x minus dou m by dou y dx du. So first we see the problem. So evaluate by Green's theorem. So integral over the closed curve C y minus sin x dx plus cos x dy, where C is the triangle enclosed by the lines y is equal to 0, x is equal to pi by 2, and pi y is equal to 2x. So these curves plotting in the xy plane. So this is y is equal to 0 is completely x-axis. Next x is equal to pi by 2. This line, this AB line, x is equal to pi by 2. So this can be written as y is equal to 2 by pi into x. It is in the form of y is equal to mx, which is passing through the origin. So this is a straight line passing through the origin. So we have to find this area R. So this R is bounded by the closed curves OA, OB, OC, BO. Okay. So by the Green's theorem, we have this condition. Integral over the closed curve C mdx plus mdy is equal double integral over the region R dou n by dou x minus dou m by dou y dx dy. So here we have to find, and okay, so given equation, integral equation is of the form mdx plus ndy. So let m is equal to y minus sin x, n is equal to cos x. So partial differentiation with respect to y for m is 1. Partial differentiation with respect to x for n is minus sin x. So we are substituting these values in the Green's theorem condition. So by Green's theorem, integral over closed curve C mdx plus ndy is equal to double integral over r dou n by dou x minus dou n by dou y into dx dy. Here the value is what? dn by dx is equal to minus sin x. So this is minus 1. So in the next step, we are substituting the values in the condition. So substituting this double integral over r minus sin x minus 1 dx dy. Here let minus common outside. So then we are getting, so minus double integral over the region r 1 plus sin x or sin x plus 1 dx dy. But here you have to observe that for it, you have to take x value is constant, x is equal to 0 to x is equal to pi by 2. For this area, lower curve is y is equal to 0 and upper curve is y is equal to x by pi. So for the double integral, so we are taking minus the asterisk integral x is equal to 0 to x is equal to pi by 2. Integral y is equal to 0 to y is equal to 2x by pi 1 plus sin x dx dy. So this we are integrating first with respect to y and substituting the upper limits and lower limits. Then after integrating with respect to x, then substituting the limits, upper limit minus lower limits. So now we are first integrating with respect to y. So this equation can be written as minus integral x is equal to 0 to x is equal to pi by 2. Integral y is equal to 0 to y is equal to x by pi. Sine 1 plus sin x dy into dx. So now integrating with respect to this. So when we are doing integration with respect to y, but there is no y term in the above equation. So, okay, this is the treat as constant function. So we are getting integration is y. For constant function, we integrate y. So here, y lower limit is y is equal to 0 to y is equal to x by pi dx. So then next step, substituting the upper limit minus lower limit in place of y. So 2x by pi minus 0. So here the 2 by pi is the constant, bring it to the outside of the integration. So that is equal to minus 2 by pi. Integral x is equal to 0 to x is equal to pi by 2. So here we have x into 1 plus sin x dx. So this can be written as, the splitting this equation can be written as, So minus 2 by pi integral x is equal to 0 to x is equal to pi by 2 x plus by multiplying x. So x into sin x dx. So this can be written as so minus 2 by pi. So integral x is equal to 0 to x is equal to pi by 2 x dx plus x is equal to 0 to pi by 2 x into sin x dx. So let the first term is equal to I1, the second term is equal to I2. So we have to find individually, then substitute in these equations. Then we will get the answer. So let I1 is equal to integral x is equal to 0 to x is equal to pi by 2 x dx. So we know that the integration of x is what? X square by 2. So the limits are 0 to pi by 2. So here the 1 by 2 is the constant. So substitute x square minus y square. X square minus. So in place of x, substitute upper limit pi by 2 whole square minus 0 whole square. So this is equal pi by 2 whole square means pi square by 4. So 1 by 2 into pi square by 4 minus 0. So this is equal, we are getting pi square by 8. Let this equation number 2. Next, let the second term, that is I2 is equal to integral x is equal to 0 to x is equal to pi by 2 x sin x dx. So we are integrating this one by bypass, integrating bypass using this condition. We have integral f of x into g of x dx. If this is equal to f of x into g of x dx minus integral of f dash of x integral g of x dx whole dx. So here let f of x is equal to x, g of x is equal to sin x. Okay, here f of x is equal to x, g of x is equal to sin x. This implies f dash of x is equal to 1. Integral g of x df is equal to minus cos x. Substitute these values in equation 3. So we get, so I2 is equal to integral x is equal to 0 to x is equal to pi by 2. X sin x dx is equal to x into integration. This is equal to g of x dx is equal to minus cos x minus of integral x is equal to 0 to x is equal to pi by 2. So derivative of f of x is 1 into integration is minus cos x dx. Limits are 0 to pi by 2. So here the minus into minus plus, okay. Next. So here minus, this is equal to minus x cos x from the above step plus integral x is equal to 0 to x is equal to pi by 2. So cos x dx. Integration of cos x is what? Sin x. So this is, so the limits are 0 to pi by 2. Substitute upper limit minus lower limit. So in place of x, substitute pi by 2. So minus pi by 2 cos pi by 2 plus sin pi by 2 minus of the lower limit 0 into cos 0. So minus sin 0. So this is equal. We know that cos pi by 2 is equal to 0. So 0 into minus pi by 2 is 0. So sin 90 is 1. Sin pi by 2 is equal to sin 90. That is 1. So 0 into cos 0. 0 into cos 0 value is 1. So into 0 is 0. Minus sin 0 value is 0. So this term is equal to 0. This term is equal to 0. This term is equal to, we will get only 1. Therefore, I2 is equal to 1. So I1, I2 values we have. So we have to substitute in equation 1. So previously we considered equation 1, that is, so pi by 2 minus 2 by pi. So this value is pi square by 4. So this value is plus 1. So we have to substitute. So in substituting the values, equation 2, equation 4, and equation 1, we are getting. So therefore, integral over C y minus sin x dx plus cos x dy is equal to minus 2 by pi square by 8 plus 1. Okay, this is the required solution. Next is second problem. So using Green's theorem, evaluate. This is also evaluate. Okay. So integral over the curve C 2xy minus x square dx plus x square plus y square dy. So where C is the closed curve in xy plane bounded by the curves y is equal to x square and y square is equal to x. But in the curves are given two parabolas. One is the parabola is y is equal to x square, and the parabola is what? X is equal to y square. So here the intersecting area. So the two parabolas are intersecting. So in that intersecting, the bounded area region R we have to find. So here by the solving these two equations, that is x square is equal to y square is equal to x, we are getting, so we are getting, so y square is equal to x square is equal to y. So we are substituting x is equal. So we are substituting y is equal to x squared. So from this we are getting x is equal to 0, x is equal to 1. Similarly, we will get by substituting x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1. Here, O 0, comma 0, here the point, intersecting point is 1, comma 1. So that is 0, comma 0 and P 1, comma 1. So the two parabolas of y square is equal to x and x square is equal to y are intersecting at 0, comma 0 and P 1, comma 1. Okay, in xy plane. Next, so given that integral equation it is in the form of m dx plus n dy. So here let m is equal to xy minus x square, n is equal to x square plus y square. So which implies, so dou m by dou y is equal, we are getting 2x, dou n by dou x is equal to 2x. So hence dou n by dou x minus dou n by dou y is equal to, so 2x minus of 2x, that is equal to plus 2x minus 2x, both are cancelled, that is equal to 0. By the Green's theorem, we have this condition, integral over the closed curve C, n dx plus n dy is equal double integral over the region R, dou n by dou x minus dou n by dou y, dx dy. Okay, so this is equal to find this area. So we will take x values, x is equal to 0 to x is equal to 1 up to here. So this is the lower curve, this is the upper curve. So for the upper curve, y is equal, we can take root x. For the lower curve, this one, lower curve is, we will take y is equal to x square. Okay. So integral x is equal to 0 to x is equal to 1, integral y is equal to x square to y is equal to root x. This value equal to what? 0 into dx dy. So 0 into something, 0. Integration of 0 is also 0. So therefore, so the answer of the problem is 0. Next, third problem. So verify Green's theorem for integral over C 3x square minus 8y square dx plus 4y minus 6xy dy. So where the C is the region bounded by x is equal to 0, y is equal to 0 and x plus y is equal to 1. So by Green's theorem, we have this condition, integral over the closed curve C m dx plus n dy is equal to integral over the region R dou n by dou x minus dou n by dou y dx dy. So by the x is equal to 0 is what? X is equal to 0 is complete y-axis, y is equal to 0 is complete x-axis. This is intersecting form at x is equal to 1, but y is equal to 1. Okay, this is a straight line intersecting at x is equal to 1, y is equal to 1. So the point A is 1, comma 0, the point B is 0, comma 1. Here 0, comma 0. So to find these, verify means we have to find LHS and RHS, both should be equal. Then only we can say that the given problem is verified by using the Green's theorem. So let, okay, it is given in the form of m dx plus n dy. So from this, let m is equal to 3x squared minus 8y squared, which implies dou m by dou y is equal to minus 16y. So let n is equal to 4y minus 6xy, which implies dou m by dou x is equal to minus 6y. So therefore, dou n by dou x minus dou n by dou y is equal to, so minus 6y minus of minus 16y is equal to minus 6y plus 16y is equal to 10y. So that is dou n by dou x minus dou n by dou y is equal to 10y. Let this equation number start. So first we find the LHS of the Green's theorem condition, that is integral over C m dx plus n dy. To find this, we have to find first OA. So this is entire OA, OB, OA plus OB plus BO. So we are divided into three curves. That is first C1. The first curve is O to A. The second curve is A to B. The third curve is B to O. So C1 plus C2 plus C3. So then we will get the complete path of the curve or straight line. So first now integral over C m dx plus n dy. This is equal integral along with OA plus integral along with AB plus integral along with BO. Let this equation number 1. So now along with AO. So along with AO, so we have O point is 0, comma 0, A point is 1, comma 0. Here y is equal to 0 is constant, which implies dy is equal to 0. Okay, dy is equal to 0. Dy is equal to 0. So y is equal to 0 and dy is equal to 0. Substituting in this condition, so 8y, here we will get 0. So dy is 0. 0 into something 0. Only we will get 3x squared dx only. Okay. So integral along with OA m dx plus n dy is equal to integral x is equal 0 to x is equal to 1, 3x squared dx. So integration of x square is what? X cubed by 3. 3 will get cancelled. Limits are 0 to 1. So upper limit minus lower limit 1 cube minus 0 cube, that is equal to 1. So therefore integral along with OA mdx plus ndy is equal to 1. Let this equation number 2 along with the first curve. Next, along with AB. So we have the straight line AB, x plus y is equal to 1, which implies we can write x is equal to 1 minus y. So differentiating on both sides, we are getting dx is equal to minus dy. So y varies from 0 to 1. Y varies from 0 to 1. Okay, y varies from 0 to 1 only. Okay, here y value is what? 1 comma 0. Here the point at a is equal, at the point a is equal 0, 1 comma 0. Yet here b is equal 0 comma 1. Y varies from 0 to 1. Okay, these values substituting in the above condition, given condition. So integral along with AB mdx plus ndy is equal. So integral 0 to 1, 3 into, here we have x square. In place of x, we are substituting 1 minus y square. So 3 into 1 y minus 1 whole square minus 8y square. In place of dx, we are substituting minus dy plus 4y. 4y plus 6y into, in place of x, we are substituting y minus 1 dy. So the limits are y is equal to 0 to y is equal to 1. So this is equal by the simplifying and taking common. So dy we are getting integral y is equal to 0 to 1, 11y square plus 14y, sorry, 4y minus 3 dy. So integrating with respect to y, so y square integration is what? Y cube by 3. Y integration is what? Y square by 2. So constant 3 into 1. So this integration is what? Y. So the limits are 0 to 1. So 11 into y cube by 3 plus 4 into y square by 2 minus 3y, limits are 0 to 1. So upper limit minus lower limit. Substitute upper minus lower. So we lower limit is 0. So just substitute upper limit. So in place of y. So 1 cube is 1, 1 square is 1, or 3 into 1 is also 3. So here 11 by 3 plus 2 minus 3. So this is equal, we are getting 11 by 3. So 2 minus 3 is what? Minus 1. By the taking LCM, we are getting 8 by 3. So therefore, integral along with the AB mdx plus ndy is equal to 8 by 3. Let this equation number 3. Next, we have to find along with BO. So along with this path, along with BO. Okay. So here, along with BO, so x is equal to 0. So that is completely y-axis. dx is equal to also 0. And y varies from 1 to 0. Okay, substitute x is equal to 0 and also dx is equal to 0. The first term equal to 0. In next term, substitute x is equal to 0. So integral along with BO mdx plus ndy is equal to integral y is equal to 0 to y is equal to 1 to 0, 4y dy. This is equal to 4 is constant right outside. Integral 1 to 0 y dy. So integration of y is equal to y square by 2, limits are 1 to 0. So substitute upper limit minus lower limit. So here 2 1s are 2 2s are. So 0 square minus 1 square. So that is minus 1. 2 into minus 1 is equal to minus 2. So let this equation number 4. So the complete line integral is equal, we have to add these 3. Okay, then we will get the complete the path. So from equation 1, 2, 3, and 4, we have integral over C mdx plus ndy is equal along with OA plus along with AB plus along with BO. So that is along with the OA is 1 plus 8 by 3 along with AB minus 2 is along with BO. So this is equal 8 by 3 minus 1. By the simplifying, we are getting 5 by 3. So next we have to check the right side condition of the Green's theorem. That is this condition. Now RHS of the Green's theorem, double integral over the R, dou n by dou x minus dou m by dou y dx dy. So by the observing the diagram, here you have to take x limits, x is equal to 0 to x is equal to 1. Next, this is the line. Okay, in this region, this is the lower curve. Y is equal to 0 is the lower curve. This is the upper curve. So you can write y is equal to 1 minus x. Okay, for the double integral, you have to take. Okay, already we find dou m by dou y and dou n by dou x also. Okay, from this condition, double integral over the region R, dou m by dou x minus dou m by dou y dx dy is equal Integral x is equal 0 to x is equal to 1, y is equal 0 to y is equal to 1 minus x, 10y. Previously we got minus 6y plus 16y, that is equal to 10y dy dx. So now we have to integrate first with respect to y, then substitute the limits, thereafter integrate with respect to x, thereafter substitute the x limits. So 10 is the constant right outside, integral x is equal to 0 to x is equal to 1, integral y is equal to 0 to y is equal to 1 minus x, y dy of dx. So 10 into integral x is equal to 0 to x is equal to 1. Integration of y is what, y square by 2. The limits of 0 to 1 minus x dx. Here we have to substitute upper limit minus lower limit in place of y. So here you can cancel 2 1 are 2 5 5 into, okay, integral x is equal to 0 to x is equal to 1 in place of y. So you have to substitute 1 minus x. 1 minus x whole square minus 0 square into dx. So this is equal to 5. Integral x is equal to 0 to x is equal to 1. So you just whole square it. So a minus b whole square. A square minus 2ab plus b square into dx. So then you have to integrate, okay, for each term. So integration of 1 is x minus integration of 2x is what? X, 2x square by 2. 2 will get cancelled. Plus integration of x square is what? X cube by 3. The limits are 0 to 1. Substitute the limits. So x 1 minus 0. 2 will get cancelled. 1 square minus 0 square. Next, that is 1. So here, uh, 1 by 3 into 1 cube minus 0 cube. So here we will get 5 into 1 minus 1 plus 1 by 3. Here plus 1 minus 1 will get cancelled. So this is by the multiplying 5 into 1 by 3, we are getting 5 by 3. So here the LHS and RHS of the Green's theorem both are equal, and this is verified. Both are same. Okay, from equation 5 and 6, we have integral over this curve C mdx plus mdy is equal to w integral over the region R dou n by dou x minus dou n by dou y dx dy. Hence, the verification of the Green's theorem completed. Okay. Next, coming to the applications of the Green's theorem. So Green's theorem has several applications in different fields, including calculating the area of the irregular shapes, determining the circulation and the flux of fluids across the surface in engineering tasks, facilitating the analysis of electromagnetism field flux in physics, assisting in environment modeling to predict challenges and movement in weather patterns, breaking down the line integrals with shorter paths, and also evaluating the line integral of the form integral over the closed curve m of x comma y x dx plus n of x comma y x dy on a vector field function. Okay, thank you. I hope you understand well. Thank you. 1 second.